In this section, we bring together the programming foundations from earlier topics and move closer to real application development. The focus is on using packages and libraries, understanding how external tools extend Python, and then applying multiple ideas together in a final mini project. This is an important transition because you are no longer just learning isolated concepts. You're building an integrated system. By the end of this section, you should be able to use Python libraries in your code, install packages with pip, read documentation to understand external tools, and build a mini project that combines multiple concepts. This is a bridge from previous sections into project thinking. You already know variables, control flow, functions, and OOP. Now the focus is on integration. Instead of writing small disconnected examples, you are now going to learn how to combine those tools into something that resembles a real application. The phrase "the whole is greater than the sum of parts" captures this idea well. What are libraries? Libraries are introduced here as pre-written code, created by others that we can import and use. The key point is that libraries save us from reinventing common solutions. Instead of building everything ourselves from scratch, we can rely on tested modules and functions for standard tasks like maths, data handling, or visualization. Why library? So, of course, to save time. Then provide tested solutions and also let us build faster. This is an important professional mindset. Good developers focus on solving the problem that is unique to their project and use existing tools for common parts whenever appropriate. Standard versus external libraries. This is an important distinction. Standard libraries come with Python and need no extra installation, while external libraries must be installed separately, usually with pip. Here are some good examples: built-in modules like math, random, then datetime, and OS versus external tools like NumPy, Pandas, and Matplotlib. You should understand this difference because it affects both setup and project planning. Here you can see the three key built-in modules: math for mathematical functions, random for randomness and simulation, and datetime for working with dates and timestamps. These examples are useful because they show that Python already includes many practical tools before we even install anything extra. Now the focus moves to commonly used external libraries. NumPy is presented for scientific computing and array operations, Pandas for data structures and analysis, and Matplotlib for visualization. These are very common tools in data-related programming, so this slide will help you see what kinds of problems external libraries are designed to solve. Data analysis, simulation, and visualization are just some real use cases. Even though it is a simple way to show it to you, but you can see that the clear sense of application areas. Libraries are not just abstract add-ons, they are like the tools that make these real computational tasks practical and efficient. So professionals rarely code everything from scratch. That is worth noting. So in real development, efficiency often comes from knowing what to reuse, what to import, and how to combine trusted tools with custom project logic. A simple example here using import math and math.squareroot. It's a clean example of library usage because the task is familiar to you and the code is straightforward. You see the import step, then the module name, import and math, and the notation for accessing the function, math.squareroot. Here is the output. The output is 4.0 float, and you can see it is for the math.squareroot 16, so it will be returning a float. Because you may expect an integer, but remember that library functions often follow their own return conventions, which is why reading documentation matters. Now let's look at the library random. So random.randint then 1 and 10, which returns a random integer between the two given bounds, the 1 and 10. So you can see that how standard libraries can support simulation-style tasks and decision-making logic as well, without us needing to constantly implement randomness manually. Now let's look at datetime library. So here you can see the import datetime followed by the datetime.now. This is a useful example because working with dates and times is common in logs, reports, and monitoring systems. So here you can see that the example introduced another important import style, importing a specific class from a module. This slide ties the built-in examples back to practical tasks. Math supports calculations, random supports simulation, and datetime supports time tracking. That makes the lesson less about memorizing module names and more about recognizing when each tool is appropriate. Now we will move from built-in tools to external ones. pip is introduced as Python's package manager and as the tool used to install external libraries from PyPy. This is a critical concept for you because you need to understand that external tools are not automatically part of Python and must be installed into the environment first. The terminal for installing a package. It shows pip install numpy and the typical terminal message during installation. This is a nice practical demonstration for you because you can see that installing a library is a command line action, not something done inside the Python script itself. It also introduces PyPy as the source repository for packages. This slide highlights two practical issues. pip requires an internet connection to download packages, and installations are global by default unless a virtual environment is used. That is important because it starts preparing you for why environment isolation matters in real projects. The common issues are generally that package not found, version conflicts, and permission errors. These are very realistic issues. So it is good that this slide is including them. So it is going to teach you that installation failures are not unusual and usually have identifiable cases. How to fix the issue? The solutions would be check spelling, check the Python environment, and try upgrading pip. I would emphasize here that many setup problems are not deep bugs. They often come from environment confusion, package naming errors, or outdated tooling. Here you can see that numpy with import numpy as np, creation of an array with np.array 1, 2, 3, and printing the array. It is a classic beginner numpy example and also introduces aliasing with as np, which is a common convention students will see often if you are using this. The output is shown as 1, 2, 3, and you can see that numpy arrays display without commas between elements. This is a good detail for you to note because it shows that numpy arrays are not the same as plain Python list, even if they may look similar conceptually. Here we are going to demonstrate matplotlib.pyplot with a simple line plot. The code imports matplotlib.pyplot as plt, plots x and y values, sets the title and axis labels, and calls the plt.show. This is a very useful example for you because it shows how libraries can add powerful capabilities, like visualization, in just a few lines of code. Libraries extend Python's power. This is the core message of the library section. Python by itself is useful, but libraries expand what it can do dramatically. That is why learning to work with libraries is such an important step in becoming productive with the language. This is giving you 3 good software development habits. Choose the right tool for the job, prefer stable and well-documented libraries, and avoid premature optimization. These are mature design principles. This will help you to understand that good programming is not only about making code work, but also about making thoughtful choices about tools and complexity. Now the lesson is going to introduce a very real practical issue. Different projects may need different versions of the same package, and global installation can create version clashes. This is one reason why project setup matters and why careless installation can break code that used to work. Virtual environments are introduced as a solution to dependency conflicts. They isolate dependencies for each project, help reproduce setups on different machines, keep the main Python installation clean, and allows safer experimentation across versions. This is a very important professional workflow concept. Now let's create a virtual environment. The example Python /m, then this venv, this, and then myenv is showing you how to create an isolated environment. The explanation here for it is that it creates a folder with a fresh Python installation. You are going to often use this command without understanding what it actually does. So this is to make the setup process more concrete. Now, how do we activate the environment? It shows you the activation commands for both Mac OS or Linux and Windows PowerShell. This is important for you because creating the environment is only the first step. It must then be activated so the package installation and the script execution happens inside the isolated context. Looking for myenv in the terminal prompt is practical confirmation tip. This is to reinforce the purpose of virtual environments that guarantee an isolated project setup and prevent conflicts. It is a concise way for you to just remember the benefit. Without isolation, dependency issues can become confusing and hard to debug. Now we are going to shift to another developer habit, reading documentation. The reasons given are actually the strong ones. So documentation teaches correct usage, reveals extra features and parameters, and helps avoid implementation mistakes. This is especially important when working with external libraries, because we are using tools we did not write ourselves. So what to look for in docs? I'm going to now give you a very useful reading strategy. Identify the function or class name. Check parameters and return types. And look for examples and edge cases. This is an excellent advice for you because you often might see read the docs, or others will tell you read the docs without knowing what information they are actually supposed to extract from that. Here is an example that is np.mean and in bracket r on a numpy array 1, 2, 3, 4. So this is a nice documentation focused example because it highlights a specific function from a library and demonstrates how it is used in practice to compute an average. So remember, good developers read documentation. That point is worth repeating because many beginners assume strong developers memorize everything. In reality, strong developers know how to find reliable information quickly and interpret it correctly. Now we are going to mark the move into the project design. The process given is excellent here. Define the problem, break it into parts, assign functions and classes, and choose libraries. This is a strong planning framework because it reminds you that coding should begin with structure and decomposition, not with random implementation. The pipeline example is simple and effective. Read the data, process the data, and output the result. This is a very common software pattern, especially in analytics and monitoring. It helps you see how a project can be broken into stages before any code is written. This is to tie the previous topics together by naming loops, functions, and OOP as tools that can be used in the project. That is useful because it is going to remind you that mini project is not introducing entirely new programming foundations, it is combining what you have already learned. Plan before coding. Planning first reduces confusion, supports modular thinking, and makes coding more purposeful. It is a very important habit for you to develop early because rushing into code often leads to messy structure and avoidable mistakes. Now we are going to see how to integrate concepts, how data structures, functions, and classes each contribute to a larger system. Lists and dictionaries help organize data, functions package logic, and classes model entities and state. It is a good conceptual reminder that bigger systems emerge from combining these smaller building blocks thoughtfully. The example calculate total data returning some data is simple for you, but it reinforces the point that functions encapsulate reusable logic. Even small functions can make a program more modular, easier to test, and easier to read. The slide is giving you two concise principles: build the system step by step and compose small testable parts. This is a very valuable design mindset. Large projects are much easier to manage when they are assembled from smaller components that can each be understood and verified independently. Why do we need to test? So small parts are going to go into the big system. So we have to test the small parts. It summarizes the logic of modular design very nicely. You should come away with understanding that strong systems are usually not built as one giant block of code, but as organized collection of smaller parts working together. That's why we will be testing. The testing is to explain to you, right? Why it matters. It catches errors early, checks correctness, and allows safe refactoring later. That is very important because students often treat testing as optional, but testing is what gives confidence that the system still behaves correctly as it evolves. Now a simple test example. So assert here, assert calculate underscore total, then the array 1, 2, 3, and then if it's equal to 6. And then it prints a success message. It shows that assert is a built-in way to verify a condition and stop the program if that condition is false. This is a nice first step into testing logic. Now I'm going to give you some debugging tips. So here are 3 habits: add print or log statements, check control flow and variable states, and test small units before full integration. These are practical and realistic tips that you can use immediately. It also reinforces the modular mindset for you. Smaller parts are easier to debug than an entire system at once. Now let's get into the final mini project. So this is, let's take an example of a simple energy monitoring system because it's a good project choice as it is concrete, relevant, and also simple enough to demonstrate how different concepts come together in one integrated workflow. The project goal is very clear: track energy usage per room and identify high usage. This is a strong problem statement because it is simple, measurable, and naturally suited to object modeling and a conditional logic. So let's define the room class with attributes name and energy along with a status method that returns high if energy is above 150 and normal otherwise. This is a very good application of OP because the room is treated as a real entity with state and behavior. not just as a loose collection of variables. Here, the project adds two room objects to list and loops through them, printing each room's name and status. This is a strong integration slide for you because it combines object creation, list data structures, iteration, and also method calls in one short example. It shows how different pieces of Python work together inside as a mini system. The output shown here is room 1 normal and room 2 high. The explanation is important for you. Room 2 is flagged as high because its energy value is 200, which is greater than the threshold of 150 in the status method. This confirms that the project logic is working as intended. Now we are going to add file handling to the project by writing each room's name and status to report.txt using with open, then report.txt, then w as f. This is a strong final integration step because it brings together OOP, loop, string building, and file output. It also reinforces the best practices of using with so the file is properly closed. So now I'm going to show you the summary. So the concepts used in this project would be OOP, loops, function, and file handling. It is a useful reflection point for you because it helps you see that mini project is not one isolated topic. It is about combining multiple data and ideas into one working program. So three major takeaways: libraries extend Python beyond the basics, real projects combine distinct concepts into complete systems, and effective development depends on planning and modular design. This is a closing summary for you. So to capture both the technical and the workflow lessons of this section. So now, using real data sources like CSV, JSON, and SQL, explore advanced libraries such as Pandas, Seaborn, and Scikit-learn. Expand into dashboards or APIs and improve testing and documentation. I hope you understood how to start Python, and now it's just you need to keep building.